We just went through classical mechanics, normal and shear stress, My over I, VQ over IT, and decided that that would not be applicable to reinforced concrete beams, A, because of the shear reinforcement, and B, because the concrete beams will crack. Next, what I want to do is talk about some observations that have been made about the effect of shear span. And the first thing I want to talk about is simple diagonal tension. And we're going to define shear span as the distance of a point load from a support, and this will be shear span right here. And typically, you want to normalize a shear span relative to the height of the beam. And in reinforced concrete, we use the structural depth in all our equations. So instead of H, I know that's the height H, we're going to normalize everything to D, which is, so I've drawn that as H. So D is the distance to the steel, the reinforcing steel. So, but D and H are about the same. And when this distance of the point load from the support is more than 3 times the depth of the beam or 4 times the depth of the beam, you're going to get something called simple diagonal tension failure. And let me try to explain this. If you have ever shot a BB at a plane of glass, let me clean this up. Okay. What will not happen, it's not like a punch. It will not punch out a cylindrical piece of glass. That will not happen. The BB will not poke out a cylindrical hole in this sheet of glass. What will happen, so that won't happen, what will happen is a cone will pop out. So you'll get a cone of glass that will pop out. And if you've ever done this, or if you've ever seen a rock hit a piece of glass or shot a BB at a window, you would see on the back side a cone of glass pops out. And why is this? If you do look at a stress block right here where you think it's going to shear out, you would get this. This is a case of pure shear, only shear, no bending moment. And this, to draw the Morse circle for that, on one face is shear and no axial stress. On the other face is shear and no axial stress. And that's the Morse circle right here. And the Morse circle is centered around the origin. And so you can see that this stress, if that's the shear stress, that's the radius, so that stress would be tau 0. The key thing in this is that the angle to the principal tension axis on the Morse circle is 90 degrees. And so in real life, remember, 90 degrees equals 2 theta. So in real life, the angle to the maximum tensile stress is 45 degrees. And that's what this is. You'll see a 45-degree cone pop out. And you can understand that by looking at this stress block here. So I've taken the lower triangle of that stress block, and I've drawn that. And you can see that those two equal shear stresses are pulling diagonally down and to the right. And across that, the diagonal, there's a traction vector that's going perpendicular to that, and it'll be pure tension. And so what happens is this orange cone is popping out in tension. And that's why at 45 degrees, you get a tension crack. And what happens in concrete, I'm gonna do this, and I'm gonna put tension to the left, compression to the right, because concrete's so bad in tension. And when you increase the shear stress, that will happen. And Every time the Mohr circle hits this envelope here, okay, I'm gonna change that color. Anytime your Mohr circle, you increase the load, and anytime the Mohr circle touches the blue line, you'll have failure, okay? And what happens right here for pure shear, this circle, pure shear, let me blow that up. And when you get pure shear, this is the Mohr circle, okay? And let me exaggerate, drawing the failure envelope. The blue line is like this. This here is the shear strength, and this is the tensile strength. Your Mohr circle will hit this tensile strength before it hits the allowable shear strength every single time. It's extremely difficult to purely shear concrete. We'll talk about a case where you can do that. But typically, you're going to fail in tension, and this tension happens along this diagonal. And that's why we call it diagonal tension failure. To summarize, you will have this 45-degree crack right here. That's where it starts. That 45-degree crack will happen in pure diagonal tension as long as your load is more than 3 to 4D away from the support. And that's called simple diagonal tension failure. As you bring the load closer, you move it closer to the support, you move the load closer to the support, and you're now somewhere between 1 depth to 2.5 depths away from the support. This diagonal tension happens, but as the crack goes towards the surface, there's this compression zone around that load, and there's also compression due to my over I, and the crack will arrest. It won't go through all the way through the beam, and you keep increasing the load, and eventually this will just explode or crush in compression. And so we call this kind of failure a shear compression failure. As the load moves in closer, you switch from simple diagonal tension to shear compression. You get the shear crack, it stops, and you finish off the beam by a compression failure in a compression zone. Now, when you get very close to the support, so A is less than the depth, what happens is, I misdrew that. The load points down almost directly to the support, and it's like you have two compressive loads opposing each other, and you get a splitting tension failure. If you've ever done one of these split cylinder tests, like this one here, you know what I'm talking about. So this is called a Brazilian test or split cylinder tension test. What happens is you load this cylinder like this, and it will crack exactly down that diameter in tension. These two sides start to go apart due to Poisson's ratio. It's extremely similar to using a nutcracker. So if you've ever had one of these nutcrackers like this, we don't have nuts in the US anymore because of allergies, but we used to always have these around. You would put a nut in there and you push down like that, and your nut would split. It would split. Actually, how it would split is this way. So you would look at the end view of that, and then here's your nut, and it would split like this. As you push this down, you would split the nut like that. But anyway, this is just like this. And when you bring this load close to the support, What you're doing is that component and that component of the load and the reaction, it splits the concrete just like a split cylinder test. And we call this splitting failure. Okay, but what if you don't have a point load? What if you have a distributed load? So you have something like this. What's the shear span? Is it, I don't know, you take, the resultant's at L over 2. How do you do that? Okay, we are defining the shear span as a ratio of the distance of a point load to the reaction. Okay. And that reaction, in a shear diagram, that reaction is V. Okay. What we're going to do is take the shear span ratio, A to D, okay, and we're just going to multiply it by 1, shear divided by shear. Now, if you look at this free body diagram here, I've got V, a distance A. So obviously on this cut right there is V, but this moment right here at this point is V times A. So V times A is the moment, and in the denominator we have V times D. If you see this anywhere, M divided by VD, what you need to think is that that is our friend shear span ratio. It's the shear span ratio relative to the depth D. Let's now talk about the effective shear span. We can get the equivalent A for any kind of load as long as you know M and V. As you go from, remember this is diagonal tension, diagonal, let me write that again. This is diagonal tension. This is shear compression. And this is splitting. As you reduce the shear span, you shift from diagonal tension to shear compression and then the splitting, the shear strength increases. Having a shorter shear span increases the shear strength of your beam. Okay, that is probably the one behavior of shear you need to know. Next, we'll go into how ACI, the American Concrete Institute International, has codified these things. That will be the next lecture.